Okay, so good afternoon, everyone. I'm here to talk about a satellite telemetry analysis system we developed at INPE. This is just an outline of the presentation. Just starting counting here to don't lose time. Okay, so a little background about what we are trying to solve. Then I'll go to describe this package called telemetry analysis, some examples, what was not so great, and some byproducts, and then conclusions. Okay, so for those who do not know me, my name is Ronan Arraes. I'm a control automation engineer with PhD in systems and control. Since 2013, I am with the space system engineer department of INPE, the National Institute of Space Research in Brazil, where I am the mission architect of the Amazonia 1 satellites and the technical lead of the attitude and optic control subsystems. And in Julia, I developed some packages like satellite to box, reference frame rotation, pre-tables, and some others. So, okay. So, a little bit of background. Telemetry is all the data the satellite sends to the ground stations. But we are focusing here what we call the housekeeping data, which is those bits that tells the engineers how the satellite is, the health, the performance, and other factors. It works more or less like this. The satellite goes, pass through ground stations, send this data, use some RF. This ground station has specialized computers that take this information, decodes in a sequence of bytes. This sequence of bytes is stored in a telemetry database, which can be fetched, read, and analyzed for different specialists. This system uses a flight-proven system at INPE, a flight-proven system called AOCS, which we have been using for decades. And what it actually stores is just a sequence of bytes. At the end, in the database, you have something like this. This is a telemetry frame, a raw telemetry frame, so just a sequence of bytes. So SATCS, the software at INPE, it is responsible for storing those telemetries in a structured database, and also to record the transfer functions, because we need to know what those bytes means. So, for example, that sequence in orange there, it is the satellite X coordinate. So we have to register at some place that those bytes are the satellite X coordinate, and how we can convert those bytes into meaningful information. This is responsibility of the software called SATCS. The information about telemetry lies inside a table inside the telemetry database. For Amazonia 1, our case study, we have 2,518 telemetry, so remember this number. SATCS has a lot of GUI applications, graphical user interface applications, that provide easy access to those telemetries for both the operators and the engineers. And we are using these applications for example, monitoring the satellite during the passage. So the operator at the INPE ground control center sees something like this interface here, where you can see all a small part of the parameters, check if everything is okay, send the commands they need to send to control the satellite. What SATCS does not implement? An environment to perform mathematical operations, which is really, really important for us, especially in the attitude control subsystems, because we have a huge amount of internal values that we just cannot send in the housekeeping data because we don't have bandwidth. So we have to keep this information as small as possible, but then we have to reconstruct those information using operations, perform operations with those telemetries to verify if everything in the satellite regarding the attitude control subsystem is working correctly. So before, what we did, we used SATCS to export the CSV file, load the CSV file, and do this computation, but it was very time-consuming. I'm just giving you some example here. We had some problem we need to verify the difference between the position from the GPS receiver and the internal propagation of the satellite. So to do this, we had to obtain the two-line elements from the telemetry, initialize a SGP4 propagator, obtain the GPS data from the telemetry also. Only those two blue lines here were available at the telemetry. The other points we need to compute. And then we need to convert the GPS data from a system fixed on Earth to a inertial system, or the way around, no, like this, and then compute the difference. If you see this matrix here, only this matrix here, to compute this matrix, we have to go through all these equations with those summations and those coefficients. So there's a lot of things to do. So having an environment that we can program, that we can perform mathematical operations is very important for us with the telemetries. And implementing such complex environment inside the SATCS application is unfeasible. It was not meant to do that. So we create a system Julia with an interface that can provide, interface with any telemetry storage system. At the end, what we want to do is to fetch this telemetry and have everything in a data frame. So after we have a data frame, we can do whatever we want using all the power of Julia language and the ecosystem package. And this is how we build telemetry analysis. We had 3 goals for this package. First, we must have an API general enough that we can interface with any different telemetry storage system. It must be future-proof. It must be capable to fetching raw telemetry packages and processing into meaningful values. So basically, telemetry analysis is a package that defines an API. And if you comply with this API, you can use all the functions that we have. So this is a simple way to see it. You have a telemetry database. Every mission has its own telemetry database in any format. You even have different database for different phases of the mission, when you're designing a mission, when you're testing, and when you're flying. It can be in any format. So the first API you need to define is the source. How to transform this telemetry that has a general format into a very specific one, which is a vector of a structure that we call telemetry packet. Then what the software do is to request telemetry from a specific time interval and convert to this value, this type here. After that, you have a defined type for the telemetries. And now what you need to do is to define a telemetry database. This is not the database that stores the telemetries, but the database that stores the variables. How each part of the telemetry frame can be converted into a meaningful value. And afterwards, you get the data frame with the information you want. So just to wrap up, we have 2 APIs that we need to define to make this interface with telemetry analysis. The source that defines how we can obtain the hot telemetries, how the telemetry frame is converted to this unique format that we call it a telemetry packet, and the result will be a vector of telemetry package at the desired instance. And the database are the variables. And the variables needs to define a name, a position in that byte array. Dependencies, variables can have dependencies. For example, to process one variable, you should have the value of other telemetry. So this is you need to provide. And then how you can obtain the bits, because things can get very messy. For example, you want to pack everything, and normally the information is not byte aligned. For example, you sample a AD with 12 bits. So it's not byte aligned. It's just this part of these 2 bytes that has meaningful information. Everything you have to code here in what we call the database. So just some overall view how we do this. Every telemetry source is a structure, and you need to implement just 2 functions. The first function tells how to obtain the telemetry package. In the case of SATCS, is a connection to the database, and fetching using SQL. And the second is how to get the first is the initialization, the second is to get this information. So the first initialize the connection to the database, the second gets this information. From the database side, you have to implement two functions. The first one is how to get the timestamp of each package. Every telemetry every telemetry database design has a different way to store the data of each package. You have to provide this thing here in this function. And how to unpack this telemetry, because you have some headers and some checksums and whatever. You must be sure that the telemetry frame is valid, and we are interested only in that payload, that information that actually has satellite data. So you have to provide this in this function. For the variables inside the database, you have to define a lot of things. I don't want to go which one because it's not the purpose, but a label, a position, what's the size of the telemetry, the dependencies, the description, the enginess because the byte can be shifted and whatever, and some transfer functions that converts the raw information, those bits, into meaningful information. Like I showed the X satellite position, we have a bunch of bytes, and you need to convert to the position itself. So you provide it here. Here's some example. So here we are declaring a variable. It's called C025. We get used to those strange names, but it's how we define telemetries at INPE. It's a letter followed by a number. The third line here, I think I can show my markers, yes. The third line here is the position of the telemetry, the number of bytes, and those are the functions which we are defining here. So the first function tells where we have to cut the telemetry frame to obtain the raw information. And for example, this function is converting it to a meaningful value. This in particular is the catalytic chamber temperature. So we are converting the bits into temperature here. So this is how we register the variables in the data frame. In the database, we call one function add variable exclamation mark for each variable. This is just another example. I will not go into details, but it's the same thing, but with dependencies. What's nice in this package is once you define what are the dependencies, you just do not care if you're defining one before or after. The package will make sure that when you're processing this telemetry, all those other telemetries would also be processed before. Was all have been processed. And okay. So just the general, what is the general workflow? First, you register the source, and you configure the database for your mission. This is you do just one time for each mission you have. And the workflow is, you initialize the source, you fetch the telemetries, and you process the telemetries. I will show some examples here in a second. This is just a screenshot. I think it's small. No, it's fine. How we connect to the Amazonia 1. Amazonia 1 is our satellite. It's flying right now. How we connect to the database of the satellite. Of course, I cannot do it here because of firewall problems. But I just initialize the telemetry source, and then it connects to the database. Here, we asking the telemetry from the day 19 July of 2024 for 1 day. So we are fetching 1 day of telemetry here. You see, each telemetry is one telemetry package, okay, in a vector. And here I'm asking for processing the telemetries. These are telemetries I want, and it giving me this data frame. From here, I can use everything I have in Julia language to make analysis. So let's try to do some examples here. Okay. Nope. Okay. The first thing I'm doing is to load Amazonian 1 telemetry database. What is it? It's just a package that defines the APIs. It is registering the variables, the connection source, and whatever. As I said, I cannot perform a connection here because we have a firewall, which will not allow me, but I have these many telemetry saved here. So what I'm doing here is to load this package with just the serialized version of these bunch of telemetries here. So now let's process. Let's make some processing. Let's analyze the satellite in this day. So we call df because it will be a data frame, and we call a function called processing telemetry package. The first parameter is of course the vector, and here I need to output a vector of telemetries that I want. The satellite has a very important telemetry. It's called its operational mode, meaning that the satellite is in the routine mode, or if something happens, it changes to another mode. So I will add it here, C00. I remember those variable names because we use a lot. I know that C001 is this operational mode. So it's processed everything. And then we get the satellite was in the mission mode, the routine mode, at each time instant. But okay, we have 2,518 telemetries. I will not remember all the telemetries. So we implemented a macro called search var that you can type everything here. It searches in the available fields. So let's say I want to check the core solar sensor current. I can't remember this variable, but I know the core solar sensor is called CSS. So now I have a list of telemetries in this database that has CSS at some part. It can be in the variable, label, in the description, and so on. So we take just this first one, C002_01, and add to our data frame here. If we add it here, C002201, then now I have the core solar sensor current at each timestamp. During the development, it's also important to see those values in different formats, because here I'm just seeing the processed value, the float number, but sometimes I want to see the bits, the hexadecimal, and so on. We have this ability here to, for example, ask the telemetry in the raw format. So in this case, we get the raw format as it was in the telemetry frame. We can also have what we call the byte array, okay, for example, in binary form. So now we have all the bits, and we can analyze if something goes wrong or not, mainly during the development process. You have another ways to see it, but I just won't go into details here. But okay, so now I think you understand the process. You get the telemetries, you put in data frames, so now we can take those information from the data frames and perform any transformation of mathematical operation we want. This was the goal. But sometimes things can get very, very difficult to debug. I have already saved this lot of telemetries here. And then you just cannot see the entire picture, right? You have a lot of telemetries, a lot of data, a lot of things going on. And if you want to debug something, we can interface. And this is what is nice in Julia language. It's very easy to interface between packages once you arrive in a common object like a data frame. You can use, for example, this package called terminal pager. And if you type pipe this character here, it changes to pager. And now it takes a little bit because it has to render the entire data frame. And now you can go through the data frame looking for problems or something like that. You can even freeze some rows. I think 1, 2, 3, 4 rows, and I think 29 characters here. And then you have this way to just go through all the telemetries and see if everything is working correctly. You can have this visual cursor here, mark some telemetries, important telemetries, and then just type Y to copy. And maybe, just paste in an editor or something like that, so you can send to another specialist to analyze some important events, if it happens. You can search, for example, 3.5. I search for everything that has 3 point here is everything. So I can search for everything that has this kind of pattern. So it's very important, especially when we find a problem in the satellite. We must have this ability. And this is why it was very important, this system to use, to have this kind of information inside Julia, so we can perform all this information and verification of the status. Okay, so this is for the example part. Where is the presentation? But there was the not so great part. What was the problem? The problem was 2,518 telemetries. It would be very, very, very bad to have someone writing 2,518 functions times 3. So, of course, if the mission started together, this was developed way before the beginning of the mission. So if we have the mission from the very beginning, we can register the telemetry in the SATCS and also register telemetry in the system. Okay, it will work, but it was not the case. And SATCS uses a very strange language to define the transfer function. It uses this reverse Polish notation like this one. So if you have this telemetry called C025_01_ABS, and inside this table in SATCS you have this function here, which means sum the value of this telemetry with the summation of those numbers divided by 4. This is how we store the transfer function inside SATCS. We could develop a parser inside Julia to do this computation, but will be very slow. You just saw, I processed 1 day of telemetry in very small amount of time. So we really want to have everything coded in Julia. And here was what Julia really helped us, because it has an amazing metaprogramming capabilities. So one programmer that worked with me, he developed a package that goes through those 2,000 more than 2,000 telemetries and automatically converts the SATCS transfer function into Julia function. This was not typed by a person. It was computed, generated using Julia metaprogramming and capabilities. So we just need to create this interface between the SATCS format and the Julia format. It was not easy. It takes a lot of time. But now we can perform this for every INPE missions, no problem. We have this interface that works. And the final file with all these transfer functions in Julia has more than 53,000 lines. So it was important to have this automated. But now that we have this translation, this transfer layer, we can use for any future INPE mission that will be based on SATCS. What is good is that this kind of system generated a lot of byproducts, and this is by far the most interesting one. When the operators are looking the satellite during the passage, they can only verify very simple things, like the satellite changes the operational mode, the satellite tells something is wrong in the failure detection mode, but they cannot, because it's not easy, to check, for example, if the reaction wheel starts to degrade, if the solar panel starts to degrade, and so on. And then I think, well, we have a system in Julia that can fetch the telemetries, and then I have all the power that I can inside this programming language. So we have a server in Brazil running every day an algorithm that fetches the telemetry from the day before and performs some register analysis, like we have 8 here, but we can have a lot of, any number that we want. And if it spots some problem, it sends an email to the important people with the description of what it got, together with the data frame with some important telemetry, so the specialists can look and check, no, this is just an outlier, or no, this is an important problem I have to look for. For example, here, in this day, we have an event of a more or less high angular velocity, and then it sends this email, and then we analyze. We saw that everything was fine. It's just an outlier, but it happens every day, so it just continues happening. Okay, so conclusions. We develop a general framework to analyze satellite telemetries inside Julia. We can use for different space missions. We just need to provide this interface. We only, and very only, need to store those, register those variables, because it can be a lot of work, but only this. And we are using it daily to perform very complex operations and analysis of Amazonia 1 satellite, where Julia metaprogramming capabilities were very important. I really think that we would not be able to do this in the time we did if we used another framework or another language. Okay, thank you very much. This is what I have to talk about this satellite telemetry system. No questions? Yes.
First of all, thank you for a great talk. So you're using this operational for like monitoring the telemetry. So how is your view on like the stability of Julia for this, and like the ecosystem? Was it like hard to sell it, and is it hard to keep operational?
Hard to, sorry?
To keep it, to maintain it.
Okay. This is being using every day. We just do not need any maintenance. It's just working version after version. Was long ago the moments that Julia was breaking every week. So now it's very, very stable. I just update Julia because I update, but there is not a problem, no problem at all. And things are really working well, because after we have these kind of byproducts here, where we can spot things on satellite automatically, it kind of became a requirement for the INPE's missions. Our future missions will need to have this kind of system, and we probably use Julia exactly this system, because it's already built. So it's really important for us now.
Okay, thank you. I also have another question. Okay. So now you're talking a lot about housekeeping telemetry,
yes.
But payload telemetry, can you also reuse some of the components for that? And have you considered using Julia to process the payload data?
Yes, we can, because it's the same system that receives the payload data. It's just stored in a different database. So we can construct a system with those interface that reads from this database. I just didn't do this because I'm just worried about the attitude control subsystem. This is my field. But if there is interesting, it is possible. The interface is general enough to provide this kind of information. But it will be just a mission. Every interface will be dependent on the mission, because for some satellite you have an image. So how you process this image inside Julia? So, but you can. Yeah. But you can use the same system. At the end, we'll have this data frame with an image encoded in something, and then you just convert it.
But on Amazonia 1, you're not using.
No. In Amazonia 1, the payload data processing is in another department, and they have this own tools that do not use Julia. Okay.
So is telemetry-analysis.jl available?
No, it's not available. So, but I asked my superiors, I can make available if it is interesting. I just cannot make available the package that interface with Amazonia 1 for some reasons. But but for telemetry analysis, I can publish in GitHub. I will do this after the conference.
Okay, that's great. And for example, is it the interface? Is it generic enough that a random mission from another agency can come up and
anyone? The heavy lifting is here, where you need to somehow convert initial. For example, we use the same system in the previous phase where the telemetry was just a text file. We are doing the testing, and the telemetry from the satellite during this testing was in a text file, and we just implemented this API. So it's general enough. You can do this for every mission.
Right, and last one, if there's time, was it hard to get through the test and validation stage in order to get it?
To what? Sorry?
Was it hard to get it through the test and validation stage in order to use it for operations?
Yes, it was very hard because the number of telemetries, and what we did was mostly brute force. We went to SATCS, which was validated, export the telemetries, sent to a CSV file, did the same thing in the Julia side and compare one-to-one programmatically, but was kind of brute force. But since we have this other system called SATCS with validated telemetries that was used for all the development phases, we can trust those values. So what's more easy than starting from the beginning.
Okay, thank you.
I think, okay. É a outra?